Welcome to the second video cast on Chapter 7, Periodic Properties of the Elements. Make sure you have these note sheets out for Chapter 7 to write down some information about the periodic properties of the elements, Chapter 7. First, development of the periodic table. Make sure that you have a copy of your periodic table out. It can be a simple one like this, or it can be the Cadillac periodic table, because we're going to be referring to it the entire time that we're talking during this chapter. Periodic table was developed in conjunction with two scientists back in the 1800s, and they developed it because similar chemicals had similar properties, and they actually predicted what new elements would look like depending on what the other ones around it looked like. In Chapter 7, we're going to rationalize three different trends on the periodic table, and we're going to rationalize these based on their electron configuration, how they react, and on something called the effective nuclear charge experienced by the electrons around the nucleus. Simply stated, effective nuclear charge means that there are protons in the nucleus that attract electrons outside of the nucleus. And this attraction, one proton to one electron, means that the electron experiences an effective nuclear charge of one proton to one electron. Now, there are some confounding factors to this. If there are more electrons around the nucleus, I know there's more protons in the nucleus too, but these electrons in effect shield the attraction of this electron to this proton, and therefore this electron right here experiences a smaller effective nuclear charge, ENC, because it's shielded by these other electrons. Therefore, it's not exactly a 1-to-1 ratio. It might be more like a 1 to like 0.9 ratio or something like that, depending on how many electrons are in the way of that electron from experiencing the attraction to its proton or protons in the nucleus. Now, if all the electrons happen to be in the same energy level, all of them will experience the same effective nuclear charge because all of them are shielded the same. But if one is further out, it of course experiences less of an effective nuclear charge. This effective nuclear charge explains all three of the trends that we're going to talk about in this chapter. First trend is the size of atoms and ions. The size of atoms and ions. This picture's in your book. Atomic radii for the first 54 elements on the periodic table. The radius tells us the size of an atom. And generally, atomic radius increases as we go down, and it increases as we go to the left. You need to know, number one, the trend. Memorize the trend. Number two, you need to know why the trend takes place. Know why the trend takes place. I'll explain it to you right now. Rewatch the video 6 times if you need to, so you know why the trend takes place. First of all, it increases as you go down because you increase the principal quantum number n. In other words, you increase the number of energy levels of electrons, and I'll write it on here. Increases as you go down. You write it in your notes as well. Increases as you go down. Okay, the size increases as you go down because you add shells of electrons. Okay? Secondly, it increases as you go from right to left. Increases right to left. And the reason it increases from right to left is because there are less protons in the nucleus. And just as I said before, the less protons there are in the nucleus, the less effective nuclear charge that these electrons experience, and therefore they're easier to float away from the nucleus. If you look over here, for example, in period 3, sodium, magnesium, aluminum, silicon, phosphorus, notice how they get smaller as you go this direction. All of them have electrons in the third principal energy level, n is equal to 3. But there are more protons in the nucleus of argon than there are in sodium. So the electrons are pulled tighter and held closer in argon than they are in sodium because there's more protons in the nucleus, and these electrons can experience more of an effective nuclear charge because there's more protons there. This one electron is shielded by a whole bunch of them and only has one proton to look to, and therefore it is held looser. Okay, that's our three-dimensional picture, as on page 266 is the one I'm showing you right here. Next, radii of ions. Well, when an atom gains or loses an electron, it's called an ion. When an atom gains or loses an electron, it's called an ion. And here are the basic relative sizes of the atoms and ions, and this diagram is given to you on page number 269. Here's the general rule. If something is becoming a positive ion, it has lost an electron, and therefore it is becoming smaller. It will become smaller. If something becomes a negative ion, it has gained an electron, and therefore it will become bigger. Generally, on the periodic table, things on the right-hand side, like fluorine, chlorine, bromine, and iodine, oxygen, sulfur, selenium, looking on your periodic table, these are located on the right-hand side over here, fluorine, chlorine, bromine, iodine, oxygen, sulfur, selenium. These guys will gain electrons. They want to attain a noble gas configuration like these guys. When they do that, they get bigger. Notice the blue, bigger sphere size. Generally, things on the left-hand side of the periodic table, like lithium, sodium, potassium, beryllium, magnesium, calcium, these guys are located on the left side of the periodic table over here in the alkali metals and alkali earth metals, and even these guys over here, aluminum, gallium, indium, things like that. They generally lose electrons. By losing electrons, they'll also attain a noble gas configuration. When they lose electrons, they become smaller. Same number of protons, less electrons. Therefore, more effective nuclear charge experienced by those electrons that are left over. And so they become smaller. Notice the pink spheres are smaller than their regular size. Okay, that's the general rules. What about isoelectronic species? Well, isoelectronic means the same number of electrons. Same number of electrons. And examples of this would be Na plus 1, Mg plus 2, and Al plus 3. Those three would be isoelectronic to each other, because this one's lost 1 electron, this one's lost 2, this one has lost 3. And you can see what happens to them here. Lost 1, lost 2, lost 3. Notice what happens to their size. The smallest one is aluminum plus 3. Why? Well, because aluminum has more protons in its nucleus. Therefore, it can pull those electrons closer, and those electrons that are left experience more of an effective nuclear charge. Sodium, less protons in the nucleus, only lost 1 electron. So it's a bigger ion in an isoelectronic species. Moving on, next page, ionization energy trend. Ionization energy is defined as the minimum energy required to remove an electron from the gaseous, make sure you memorize that, state of an isolated single atom or ion. An isolated single atom or ion. Okay? Single atom or ion. An example equation for this would be Na, and then I'd have to put gaseous down here because it's in a gaseous state, and then it would form Na positive 1 gaseous state, and an electron that's lost. This would be an equation showing the ionization of sodium. Notice it's a single gaseous atom. I could also say, well, Na positive 1 gaseous would lose another electron and form Na plus 2 gaseous plus an electron. This would be what's called the second ionization energy, because it would have lost a second electron from its normal gaseous state. This trend is in enthalpy, and we symbolize enthalpy, remember, by delta H. And we have to put energy in, and therefore it's a positive value, to lose an electron, and it's always measured in kilojoules per mole. Always measured in kilojoules per mole, because it's how much energy needed to remove that gaseous, that electron from a gaseous atom in a single atom. And you can see here this table 7.2 in your textbook, shows the amount of energy in kilojoules per mole right here for a whole bunch of elements on the periodic table in period 3. Sodiums, magnesiums, aluminum. And notice how once it gets to the noble gas configuration, magnesium loses 2 electrons. Looking on the periodic table here, I'll pull this a little closer. Magnesium loses 1 electron. It looks like sodium. The magnesium plus 1 ion now loses another electron. It's going to look like neon. Now it's a noble gas configuration. It does not want to lose electrons now. And so you can see that third ionization energy for magnesium is astronomically high compared to the second ionization energy. Typical test question gives a table like this with no names of elements on it, and it says this is element 1, this is element 2, this is element 3, 4, etc. It says, what is element 3 if it's in period 3 on the periodic table? Well, now you got to know that, when its fourth ionization energy takes a quantum leap, it's got to be the one that after it loses 3 electrons, it's going to be like a noble gas. So if you know it's in period 3 here, let's see, period 3, okay, aluminum loses 1, aluminum loses 2, aluminum loses 3, it looks like neon. The fourth ionization energy is going to take a quantum leap, and you would have guessed correctly if you said that one was aluminum. That one was aluminum. So take a look at this table, 7.2 in your textbook. Okay, so what's the trend for ionization energy? The general trend is that you move from left to right, ionization energy increases. Okay, ionization energy increases as you move from left to right across a period. Left to right across a period. From lithium to neon, it increases, and notice it's in kilojoules per mole, and there's a bunch of energy there. Sodium to argon, potassium to krypton, it increases. Okay, general rule. There's a few anomalies here, right here, and right here. We'll talk about those in just a second. Okay. If you want to take a look at another diagram of ionization energies, you can take a look at this one in your textbook, figure 7.10. You can see that ionization energy generally increases as you go across the table. And then ionization energy generally increases as you go up the period too, because the electrons are closer to the nucleus. Remember, your goal in this chapter is to, number one, not only memorize the trend, but know why the trend takes place. And of course, it always takes place because electrons are attracted to protons. And the more or less they're attracted to protons makes a huge difference. Makes a huge difference. Okay? So, answering a couple questions on here. Periodic trend for first ionization energy and some anomalies. Generally, for first ionization energies, ionization energy increases from left to right across the periodic table. There are a few anomalies between, let's just look at period example. Period 3 between magnesium and aluminum. You generally say that it increases from left to right, but aluminum actually has a lower ionization energy than magnesium. And if you look on your periodic table, I'll just use this one for an example, you can see that aluminum right here has a lower ionization energy than magnesium, 578 versus 738. The reason that is because right here, aluminum has that electron configuration of, outer electron configuration now, of 3s2p1, whereas magnesium was just 3s2. Notice its outermost electron is in the highest energy state. In the p orbital, and it's easier to remove that one. So the first common anomaly occurs between this group 2A and this group 3A. This is probably a good time to just pause for a second and talk about the makeup of the periodic table, because the periodic table has a number of different ways of naming its groups and families. I'll just put this one down here because you can see the whole thing at one time. I'll zoom in just a little bit again. Certain periodic tables number their groups as 1, 2, 3, 4, 5, all the way up to 18. 1 through 18. That's the easy way to know them. Other periodic tables number their groups as 1A, 2A, skip these guys, call these guys 3A, 4A, 5A, 6A, 7A, and 8A, and then come back here and call these the B's. Other periodic tables call these guys 1A, 2A, these 3A, 4A, 5A, all the way up to 12A, and then call these the B's. Now, which one is correct? We're not here to judge, we're just here to try to explain. So, what I like to do is get rid of the A's and the B's stuff and assume that the A's and the B's stuff that's used in our book just mean what are called the representative elements, which are the S and the P blocks. The S's and the P blocks. And then, for the most part, talk about groups or families as 1 through 18. 1 through 18. And name them if you can. Like these, the alkali metals, the alkali earth metals, halogens, noble gases, etc. Okay? That's generally the way that it's done. So these guys, group 2 and group 13 right here, generally have an anomaly between them because of their electron configuration. The other anomaly that takes place is between the nitrogen group and the oxygen group, group 15 and group 16, or sometimes called 5A and 6A, depending on which numbering of the periodic table system you like. Notice how it goes down just a little bit, down just a little bit, down just a little bit. The reason for that is in the electron configuration, and the way to see this best is to write the orbital notation. For nitrogen, the outer electron configuration is 2s2, if I draw the configuration one arrow this way, one arrow this way, and then 2p3. If I draw the boxes, there would be one electron in each box of the same spin. And then for the oxygens, it would be 2s2, 1 electron, 2 electron, then 2p4, 1, 2, 3 boxes, 1 electron, 2 electron, 3 electron, 1 paired up. It's this paired up electron, that offers lots of extra repulsion because it's got to pair up with a like charged electron that causes it to be easier to remove an electron from oxygen, sulfur, and selenium than it is from nitrogen, phosphorus, and arsenic, because these guys right here have a half-filled sublevel, which is a little bit more stable than when you have to start to pair them up. So those are the anomalies, and if you're following along with this, you wanted the 3D picture, which you've seen a whole bunch of, and it talked about the few anomalies along with ionization energy. Next, electron affinity. Electron affinities are usually the energy released, sometimes gained, when in a atom in its gaseous state, once again, just like with ionization energy, in its gaseous state, gains an electron. Okay? Notice it's got to be in its gaseous state, it's got to be the atom, just like it was with ionization energy when it gains an electron. The trend is also an enthalpy measurement, so it's a delta H, and it's usually given in kilojoules per mole. And generally they're exothermic. For things on the non-metal side of the periodic table. I'll zoom this out just a little bit so you can see the whole trend. You can see that these are negative over here for fluorine, chlorine, bromine, and you can see that it generally becomes more exothermic to the right. There are some anomalies once again. Notice the anomaly here between carbon and nitrogen. Nitrogen, because of its half-filled sublevel, does not necessarily want to gain one because of that repulsion that oxygen would have. Same thing here with lithium and beryllium. Beryllium, half-filled sublevel, doesn't necessarily want to gain an electron to look like boron, because then it's going to have that one electron in the p orbital, that's out just a little bit further, from what the s orbital is. Okay, so electron electron affinity is generally given on page 286, and the trend is generally more exothermic to the right, generally more exothermic to the right, and generally more exothermic up. More exothermic as you go up a period on the periodic table. So those are the three trends you got to know: ion size, or atomic size and ion size, and then ionization energy, and then electron affinity. A couple more things about metals, nonmetals, and metalloids. A couple other trends on the periodic table. First of all, here's a picture of the periodic table and increasing metallic character. Notice metallic character increases as you go to the left and generally increases as you go down. If I zoom out just a little bit more, you can see the different colors, and you can see that the greenish ones over here are nonmetals. The purple ones right here are called metalloids, and then everything else is a metal except for hydrogen over here. Notice aluminum is a metal, and notice polonium is a metal, even though it borders the staircase. Otherwise, everything else that borders the staircase is a metalloid. What are the general trends for those, or what are the general properties, I guess I should say? We discussed them pretty much in the PowerPoint. Metals are malleable, they're ductile, they conduct electricity, and they have lots of good free electrons. They generally want to lose electrons. Nonmetals generally want to gain electrons. They're not malleable, they're not ductile, they're usually brittle. They usually do not conduct electricity. Metalloids do a little bit of both. They're usually semiconductors. Group trends, well, you should know the names of the groups, first of all, and then after you know some of the names of the groups, you should know a little bit about each one of the groups. So I'll show you just a few of them here on this periodic table. First of all, group 1, called the alkali metals. They generally have +1 charges. These guys +2 charges. These are called the alkali earth metals. Transition metals in the middle over here. Over here on this side, these guys are generally called the chalogens. These are called the halogens. And they generally have a -1 charge, although they can be other charged sometimes, especially in oxyanions. And then the noble gases right here. Generally unreactive. These guys generally want to get electrons. Notice how they put H-1 right here. It can act that way when it's with a metal. Hydrogen over here, when it's with a nonmetal, is always +1. You see these guys famously exothermic with water. Calcium, strontium, and barium will react with water, but magnesium and beryllium will generally not react with water. Other group trends to know, we touched on them mostly in the PowerPoint packet. I'd encourage you to take a look at some of the reactions in your textbook that happen. Some of the reactions, like for instance when sodium reacts with water, what happens? Well, it's a single replacement reaction, and so what do? You get some NaOH, which is now aqueous. When you're writing the net ionic equation, make sure to split it up into Na plus and OH minus, and then it also forms some H2 gas, which gives it its famous flame in its exothermicness, because it lights the hydrogen on fire and therefore it reacts and explodes. A couple other reactions you probably should know are a metal oxide and water. So if you've got something like K2O and it reacts with water, it's going to form a base, in this case KOH. If it's a non-metal oxide, like say for instance SO2, this is a good example to show you that it's going to make an acid, and the sulfur should stay in its same oxidation state, so it would form H2SO3, which is a weak acid, which you wouldn't want to split up. This one, of course, you would want to split up when it's aqueous because it's a strong base, writing the net ionic equation. You should be good at writing metal oxide, non-metal oxide equations just by knowing that is how they typically react. So good luck with your periodic trends and Chapter 7, periodic properties of the elements. Know the trends, but more importantly, know why the trends happen.